And then just when you get used to that, I'm going to take that drawer out. I'm going to put hexabucks in. And that drawer only has values of 1s and 16s. And you're going to have to give out change to the customers, and always give the customer the lowest number of bills possible. If you needed to give a customer $99 and change and you gave them 99 ones, they won't even be able to close their wallet, and they'll be mad at you. And I'll be mad at you because the customer's mad at you. And so we always give them the smallest number of bills possible, because that's the polite thing that we do. So let's talk through how I would give out change if the drawer is decabucks. It's decimal values of 1s, 10s, and 100s. If you need to give the customer 11 in change, what would you give them? A 10 and a 1, right? That's very easy, very straightforward. Great. Now, I'm going to take out that decabucks drawer. I'm going to put in binabucks. Yeah, congratulations, folks. You just converted decimal 11 into binary. It's B, right? Because we don't have the number 11 in hexadecimal. It's a B. Now, if it's a hexadecimal value of 1, 1, the value is 17, right? But that's a totally different context. Yeah. All right, cool. How's everybody online? Everybody doing good there? And I'm missing the context of Annette saying no. I'm going to assume that everything is, that there was no meaning something was bad. Everybody good. Awesome. Folks are typing. Give folks a chance to type. James likes the explanation. Awesome. I wish I could take credit for this. Keith himself came up with this example. And I was floored when I first saw it, because I'd worked with these numbering systems for a long time. And when he created this, I was like, this is just so easy to understand. Now, let's do another one. In this case, we've got the binary value of 10101110. How would I calculate what that decimal number would be for binary? Is I just simply add up the values where there's ones, right? There's a 1 in the 128 spot. Where's my pointer? Where'd it go? There we go. There's a 1 in the 128 spot. There's a 1 in the 32, 1 in the 8, 4, and 2. If I add all those up together, I get a decimal 174. Cool. Now, what if I want to calculate the hexadecimal value? I could do it two different ways right now, right? Because I know what the decimal number is, and I also know what the binary is. Well, you could go from decimal to hex by simply asking, how many times does the number 16 go into 174 without going over to determine that high number, that high nibble? But that's kind of clunky and inelegant. It's guessing how many times and then asking yourself, am I right? I don't like it that way so much. The other way that we could do it, which is a much more elegant solution, is to do it by nibbles. So if we're doing division, I would take 174 and say 16 would go in 10 times, probably. 10 times 160, and then 174 minus 160, 14 with the remainder. Okay, 14 is lower than 16. Yeah, it's 10. Or the other way is to just do our nibble values. We've got 1 in the 8 spot, 1 in the 2. So 8 plus 2 is 10. And of course, we can't put 10 there. So we put the letter A. And then I do the low order nibble where I see there's an 8 and a 4 and a 2. There's no 1. And so 8 plus 4 plus 2 would be 14, which is E. Now, one of the things that you'd probably notice about this example so far is that in the first example, Keith put the hexadecimal B in lowercase, and in the second one, he did uppercase. That's perfectly fine. Case doesn't matter here at all. Keith actually, he made it like this just so we could prove a point. That doesn't matter if it's uppercase hexadecimal, lowercase hexadecimal, the value is just the value, right? Now, let's go ahead and do one more. Now we've got hexadecimal 17. In order to calculate the decimal number, that's pretty easy. It's just 1 in the 16 spot. So 1 times 16 is 16 plus 7 in the 1 spot. And so 16 plus 7 is 23. We get decimal 23. And then I could either, because I've got the hexadecimal 17, I've got the decimal 23, I could either convert from hexadecimal to binary or from decimal to binary by giving out change, right? And either way is fine. So in the case of using the hexadecimal characters, we've got a 1 in the high order nibble. And so it'd be 0, 0, 0, 1. And then a 7 in the low order nibble. And so that'd be 0, 1, 1, 1. We'd have no 8, but we'd have 4 and a 2 and a 1. So either way is fine. How's everybody doing now? Doing good? We're just doing repetition now, just a little bit of practice. And the reason we're doing a little bit of practice is guess what our lab is in just a little bit? Yeah, we're doing these conversions. And so let's go ahead and do a couple more for practice. I've got hexadecimal 0F. Well, that can be pretty easy to calculate as far as the bits go. It's just all zeros for the upper order nibble and all ones for the low order nibble. But then how do I calculate decimal? Well, I just take that F, which is 15. I could just say, oh yeah, I know that F is 15. Or I could look at the bits and say, oh, those are all zeros. And then there's a 1 in the 8, 1 in the 4, 1 in 2, 1 in the 1. I get 15. Either way, it actually, after a while, it becomes easy because you just know, oh, well, F is always 15. It's always all ones for the nibble. It's just one of those things that once you got it in your head, you've grokked it. It's just there. And every time I see F, it's 15 or it's all ones, depending on what value I'm looking at. But let's go ahead and flip them. Let's say it's an upper order F and the low order nibble is 0. Well, that would be 1, 1, 1, 1 for the F in the upper order nibble spot and a 0 in the low order. Now, if I calculated that, notice these positions are important because here 0F in hexadecimal is 15. Here F0 is 240 because it's all of those higher order bits. What we're going to do now is we are going to test that. And I am going to give you a full 30 minutes to do so. For some of you, this may have been review and you're going to get through this pretty quickly. So when you're done with the lab, you're free to go on break. I'll set a timer. And so you've got 30 minutes in time for the lab, but then we've got 20 minutes for a break after that. So once you're done, you're free to go to break. When we get to the point where we've got 20 minutes left, it's officially break time, I'll put break music on for us. Our break music today will be Postmodern Jukebox. Anybody like Postmodern Jukebox? So with Postmodern Jukebox, they are a band. So actions will be different. Joke. There are only 1, 0 kinds of people in the world. What would 1, 0 be in binary? 1, 0 in binary is 2. Kelly still does. Okay, it's like whatever. I don't want to get it. She says. All right, I'll see you all back in after lab and after break.
Goes frog goes field blows on it. Taking it and forever out of
20 minutes. It just isn't possible. this was your first time around with hexadecimal and binary numbering conversions. And for some of you, that will be useful in your jobs in the future. For others, that will be the last time you see that stuff. Now, for both groups, this lab is still appropriate because for some of you who will never see this again, that's fine. But what you learned from this is now you know that those conversions are done. You know that when you look at hexadecimal characters, you know it represents bits underneath. And so if you've learned anything at this point that's useful for our discussions going forward, is that you know what binary is, you know its relationship to decimal, and you know that hexadecimal is just representing, each character represents 4 bits. And if you just remember those things through the rest of this week, you're in really good shape. That's where we need you to be. Rennie. Ooh, Rennie asked the question, do we get into subnetting? Yes, we do. That's later today. That helps with, so Rennie is making the point that when we get to subnet masks later today, and we will, yeah, this does come back at that point. Absolutely. So in a little bit, we're going to talk about how computers network together, but let's go ahead and finish our conversation as to why this was important first. Earlier, I had mentioned that the context may be a printable character on a screen. What that's called is it's called ASCII. And ASCII is just an acronym for the American Standard Code for Information Interchange. And it's basically just a lookup table where you've got these binary values and we need to convert them into some sort of a printable character. And so we simply look those up in a chart. Let me go ahead and pull up a chart here. You've got one in your book. I also have this one that I'm going to post in Slack, and I'll put it up on the board here, where it's just the computer looks up for ASCII characters. It's just looking up what is the printable character for a certain set of bits. We have already learned on this chart that this 01000001, if we're converting it to a decimal number, if that's the context, the number would be 65. And we know that because there's a 1 in the 64, the 64's spot, and a 1 in the 1, 64 plus 1 is 65. Now, octal we don't cover in this class, and there's no point for us here to cover that row, that column, I'm sorry. But then we also know that 01000001 in hexadecimal is 41. Never say hexadecimal 41, because hexadecimal 41 doesn't exist. It's hexadecimal 41, right? And if the context is an ASCII character, it's a capital A. But notice for the decimal 65, for hexadecimal 41, for a capital A, those binary bits are the same. We've just changed the context each time. Great. So now that's basically any character that's printed on the screen, including what they refer to as non-printable characters. A non-printable character is something that actually happens, but it doesn't have some sort of a character to it, like the enter key. When you hit enter, that's not printable. It just returns you to the next line. And so everything in ASCII can be described by these binary bits. Now let's go back to numbers for a moment, because with our numbering system, we could represent any number from 0 to 255 using a byte. But what if I need a number larger than 255? Well, I just add more bytes onto that. If I need to represent something larger than 256, I can use a 2-byte number. Now, 2 bytes are representing not 255 plus 255. It's actually, let me back up for a second here. If binary has 2 values, it's a base 2 numbering system. If decimal has 10 values, it's a base 10. Hexadecimal has 16, so it's a base 16. Well, if a byte has 256 different combinations, wouldn't a byte be a 256 base numbering system? Yeah, so if I have 2 bytes, it's literally the byte on the right, which is my ones position. And then I move one to the left. Wouldn't this byte be whatever its value is times 256? So I can represent not just numeric values with 2 bytes of 255 plus 255. Every time I add a bit, it doubles the possible combinations. I can represent with a 2-byte number 65,536 different values, 0 through 65,535. Great. And so every time I add a bit, it doubles the possible combinations. As you guys notice, because on that chart, it was 1 and then 2 and 4, 8, 16, 32, 64, 128. What do you think the next bit would be? 256. What would the bit after that be? 512. And then 1024, 2048. They just keep getting bigger and bigger. So I can represent much larger decimal numbers. Now, let's go ahead and talk about what those bit values would look like. I'm sorry, these decimal values for these 2 bytes. The math is here, and I'm not going to, we don't have to go through every single example, but what you're looking at is the low order byte is whatever that value is times 1, because that's the ones position. And then the byte after it is whatever that value is times 256, because that is the 256 position. So I can represent larger and larger numbers doing these 2 bytes, but I can also represent lower numbers. It's just the first byte. I'm sorry, the upper order byte is all zeros, and then we've got some ones over here in the low byte, and so that 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0 would be 80, even though we have a 2-byte number. And 80 is a special number when we talk about networking, because whenever you surf the internet, you're looking up web pages. HTTP, Hypertext Transfer Protocol, is on something we refer to as port 80. We're going to talk about what that is later. That's why we use that's why we use 80 as the number right there. Now, if I can represent larger numbers using a 2-byte field, well, if I just keep adding bytes onto that, what about a 4-byte field? How many possible combinations could I have of a 4-byte number? It turns out that it's roughly 4.2 billion combinations. So just as I keep adding bits and doubling those values, a 4-byte field would give me 4.2 billion possible addresses on the internet, because an IP address is 4 bytes in length. Now, for us humans to understand those large numbers, we actually take those bytes, and those 4 bytes, and we separate them with dots. And so here you see an IP address that's numeric of 8.8.8.8, which means that each of those 4 bytes is representing value of 8. And I put a dot in between them. So it's what we call dotted decimal notation. We'll talk about that more when we get to networking. But a computer doesn't see an IP address as this 8.8.8.8. That's just for us humans to understand. If you actually took the binary bits and you calculated them out, the number would actually be 134,744,072. So a computer sees that as the value, as the number. And here's the math behind it. It's a lot easier for us to understand that address as 8.8.8.8, because if I tell you 8.8.8.8, and then later I refer back to it, and I say, remember that number 8.8.8.8, you say, oh yeah, that's easy for me to remember. That's a lot easier than me saying, hey, remember that IP address that was 134,744,072? You'd be like, I don't know, did you say that number earlier? So these IP addresses are a lot easier for people to understand. But you can see that they're literally just the same bit values when they're all mapped out here. And now, since our byte is a base 256 numbering system, the one on the right, the low order byte, is whatever its value is times 1, which is, the original value. The next one is raised to the power of 1. The next one is raised to the power of 2. The next one is raised to the power of 3. So it's a 256 as a base. 256 to the power of 1 is 256. 256 raised to the power of 2 is a much larger number. And 256 to the power of 3 is a much larger number than that. So we can represent very large values. Does anybody recognize that? Speaking of memorable IP addresses, does anybody know what is at 8.8.8.8? Google what? You're right, it's Google, but what's there? What did Google put there at the address of 8.8.8.8? It's their DNS. Yeah, it's their DNS. Cool. And we'll talk about domain name system later today. All right, now, there's some confusion that we need to clear up when it comes to bits and bytes, because bits and bytes, both of those words start with the letter B. And I want some shorthand notation to where I don't have to write out a bit or I have to write out a byte. So I am going to use the letter B to represent bits, and I'm going to use the letter B to represent bytes. Well, that's confusing. Well, no, it's not, because what I'm going to do is for bytes, since they're bigger, I'm going to make them uppercase B's. And bits are smaller. They're just 1/8 of a byte. And so I am going to represent a bit with a lowercase b. So 1 MB uppercase would be 1 megabyte. And 1 MB lowercase b would be 1 megabit, 1/8 the size of a megabyte. And this is where some people get confused. I see this every now and then, where somebody will post on a blog or something. They'll complain that their ISP is not giving them the speed that they say they paid for. They'll say, my ISP says I have a 32 megabit connection, and then I'm not getting anywhere near that. I'm like at 4 megabits. And it's like, well, no, wait a minute, you're confusing terms. They sold you a 32 megabit connection, and then you went to some speed website and it tested your download speed, and the download speed said you have 4 megabytes of speed. Well, 4 megabytes is 32 megabits. And so, yes, you're actually getting the speed that you think that you are. You just weren't doing the conversion from bits to bytes. So no problem at all. Now, if I could teach my wife any slide in this course, it would be this one, because she asks me questions like, hey, I've got this thing, it's 50 megabytes. Is that big? Now, putting aside an uncomfortable conversation with your spouse about size, those are the jokes today, people. My wife is asking because she's trying to do something with this file. Are you trying to email it? Are you putting it on a thumb drive? Are you uploading it to some file share? What you're going to do with the file is going to be dependent on my answer as to whether that's too big or not. If you're trying to email it, 50 megabytes is probably too big to email. But if you're putting it on a thumb drive, yeah, that's perfectly fine. So if I could teach her one slide so she could do those conversions on her own, it would be this one. But remember from yesterday, I don't talk about my work to her, and she doesn't talk about her work to me. And it's just, we stay happy that way. I tried to teach her this slide, and it didn't go well. Do you know why? Because when I started teaching it to her, I started talking to her like this. One thing you do not do is talk to your spouse like this. So, honey, this is how it works. What you've got here is, she says, don't do that. I said, do what exactly? That. Don't make that voice. Don't do that voice. Okay, fine. But it's perfectly fine for us to talk like this in this classroom, right? So now let's talk file size. Let's talk about how many bytes makes up a file. If you've got 8 bits, it is 1 byte, and that would make 1 printable character on a page if you're printing it out in ASCII. Okay. Now, a kilobyte is roughly 1,000 bytes. It's 1024. And now that we understand those conversions, you know where 1024 came from. It was one of those multiples of 2. And so 1024 is technically the size. We just say roughly 1,000. We're just rounding the number down. So a kilobyte would give you roughly 2 to 3 paragraphs of text if you printed it out in ASCII characters. Now a megabyte is 1,000 kilobytes. And if you were to print that out, it would make 873 pages of text. Wow, so those numbers, those values are going up exponentially. But if you take a gigabyte, which is 1,000 megabytes, if I print that, that would make roughly 894,000 pages of text. And a terabyte is 1,000 gigabytes. And if I were to print that out, that would make 916 million pages of printed ASCII characters. To give you an idea of what the size of a terabyte would be if we printed it in ASCII on paper, imagine a whole pallet of paper. So you've got a big wooden pallet, and on that pallet you have 40 boxes. We call those cartons. And inside of each box is 10 reams of paper. Each ream of paper has 500 sheets. And so you've got paper wrapped in paper and then put in a paper box. Why we wrap our paper in paper and put it in paper is beyond me, but that's how we do things. It seems inefficient, right? So now I have a pallet of paper that has 200,000 sheets that I can print. How many of these pallets would I need to print a terabyte of ASCII text? Just about, 4,500 pallets. Now, if I saw 4,500 pallets of data leaving my organization, going out the back door, I'm going to notice that, right? Well, what if the information is digitized, not printed? A terabyte of data can fit on a thumb drive that you put in your pocket. Ooh, that's a lot of data walking right out of your facility in somebody's pocket. So the power of computers with this binary is the fact that we can have lots of information stored in very small spaces. Excellent. So now we're talking about the fact that we needed to have a context for those ones and zeros. And I said the context is defined by software. And the software is in the form of an operating system. An operating system has a central component called a kernel. This kernel is the smallest part of the operating system that's needed to run a computer. And the kernel is what the hardware starts to get its instructions on how to act like a computer. The processor is just adding values together, and the kernel gives it instructions on how to do that. So when you turned your computer on in the morning, electricity started flowing through the circuits, and there was this small amount of firmware, which was just some instructions that was embedded into a piece of hardware that said, this is how you start as a computer. You need to go to the master boot record, and the master boot record on that hard drive will tell you where to find the kernel of the operating system. And so then the operating system starts. This hardware gets its instructions on how to be a computer. And the operating systems that you know and love are, for one, there's Microsoft Windows. Windows is the most common operating system for desktops and laptops. It's at over 75% of the market, which seems awful dominating. But at one point, Microsoft Windows had 95% of the market. They have lost over the last 20 years. They have lost a lot of market share to other operating systems. What are the other operating systems? Well, the lion's share of that loss went to Mac. So Mac OS, made by Apple, as a competitor to Windows, they represent about 16.5% of the desktops out there now. So they took away most of that market away from Windows. Now, Windows can be used as a desktop or it can be used as a server. The only difference between a desktop and a server is that I sit at a desktop operating system and I type things, I check the email, I surf the web and all of that. And so this is my desktop machine that I'm working on. Well, the only difference between a desktop and a server is the server is running an operating system somewhere where I'm not sitting at it. It's just accessed by me through a network. So remotely, I'm working with that piece of equipment. And so a server in this case would be I go to a web page, or I authenticate, or I am checking my email. That's the server, the other machine someplace else on the network. And so Windows, yes, it can be used as a server, and it's almost a third of the server market. Well, whereas the rest of the server market is in Linux. Linux comprises only about 2% of the desktop market. So it's very rare that people are using Linux as a desktop. But Linux dominates in other areas. For one, it's almost always a Linux server that you're using when you surf web pages. Almost always. And so today, if you did anything on your phone, you interacted with a Linux server, almost guaranteed. Now, Linux is also the operating system, a Linux-like operating system, that it was used to make the Android operating system. And so if you've got an Android phone or a Chromebook, it is running Linux under the hood. That's the kernel. And if you've used any IoT devices today, you turned on a smart TV, or you've got an internet connected toothbrush for some reason, or a light bulb, almost always that's Linux as well. And oh, by the way, Mac OS is a Linux-like kernel as well. So the world is divided between Windows and Linux-like operating systems. Cool. So now we have this operating system that defines how the computer works as a computer. Let's talk about the different types of components we have in a computer to talk about how the computer can store and process that information. First, I have two different storage devices on my computer. I have this hard drive. This hard drive is it's a spinning disk inside of this piece of hardware, and there is a head that floats right above that disk. And so the disk spins like a record player or a CD player, and that head can read and write the zeros on that disk. And what this hard drive does very well is it can store a lot of those ones and zeros. In this particular hard drive, it's 500 gigabytes of data storage on this small device. That's what hard drives do real well. That's their superpower. They can put a lot of data on this disk. Now, your computer also has another type of storage for those ones and zeros. It's called RAM. Now, the RAM works just like the hard drive as far as being able to, I can write ones and zeros to the hard drive. I can write ones and zeros to the RAM. I can read ones and zeros from the hard drive. I can read ones and zeros from the RAM. Why do I need two that are doing the same job? Because the RAM does it a little differently. For one, instead of having a spinning disk, I store all of my ones and zeros in computer chips here. RAM, I can read the ones and zeros a lot faster off of RAM than I can the hard drive. I can write ones and zeros a lot faster in RAM than I can on the hard drive. Now, the RAM, because of the way that it works, it's more expensive. In this case, I have a 500 gigabyte hard drive. Here, I have a 2 gigabyte stick of RAM, and these two cost almost the same amount of money. Now, why in the world would I spend so much money for this? Because it's fast. I am going to use the ones and zeros on my computer in RAM, and I'm going to store them on the disk. So the disk drive is my storage, and my RAM is whatever ones and zeros I'm working with right now on the computer while it's on. The other thing that is a constraint for the RAM is that when I turn off the power of the computer, the ones and zeros in RAM just go away. If there was any data stored in RAM, when I turn off my computer, I turn it back on, it's no longer in RAM. That's okay, because when I turn off the power to the computer, the ones and zeros are still on my hard drive, right? So I store my operating system, I store the kernel, I store all of my files on the hard drive. But when I go to use them, I use them in RAM by reading them off the hard drive and then writing them up into RAM. How that looks is, let's say I've got a program like Microsoft Word. MS Word is just a file that's on the hard drive that's executable, means it's runnable. So the operating system will interpret those instructions to create a screen where you can type documents, you can open new documents, you can create new ones, you can save them. And so I double click the icon on the desktop for MS Word opens up. When it opens up, it's just simply reading that executable file off of the hard drive and writing it into RAM, because it's a lot faster to work within RAM. All right, so now I'm running Word. I have a file that's sitting on the hard drive and I want to open that file. So I click the open icon and then I choose that file. When I choose that file, the file that was on the disk is also written up to RAM. So now I have two copies of each. I have a copy of Word, the executable on the hard drive, and the file, but I also have a copy in RAM and the file in RAM. So both are in two places at this point. Now, as I type on my keyboard, my keystrokes are interpreted by the CPU, that central processing unit, to create new text, and I'm editing my file. While I'm editing the file, it's being edited up in RAM, but it's not being changed on the hard drive because that would be too slow. Every time I hit a key, that I was editing the one on the hard drive, because that's very slow. And so all the changes are being made in RAM. Have you ever been working on a computer, you're working on a document, and all of a sudden, pop, the power shuts off, and now you lost your changes in your document? That's because the copy that was up in RAM got destroyed, because remember, RAM needs that electricity. And once the power turned off, whatever changes you made in RAM, that was lost because the copy on the hard drive wasn't modified. But I am going to do the right thing. I'm going to save this file. When I click the save button, that for some reason is still the old floppy disk. I still don't understand why in 2023, the save icon is a technology that we haven't used in decades. But of course, I brought one with me because I could. I got my little bag of tricks over here. I've got a floppy disk. I have no idea what's on this thing anymore. I'm assuming it's still this Dell RAID array software here, but it's disk 5 of 5, and I don't have the first 4. And I don't have a drive to plug this into, but this is another data storage. And so that's why the save icon is this disk. I'm storing it on a disk now. When I click save, the copy that was in RAM is now written to disk. And then I close out of the document. When I close out of the document, we destroyed the copy that was in RAM, but now I have a copy that was modified on disk. I exit out of Word, and now Word is removed from RAM as well. But I still have my now modified document and MS Word on the hard drive. I can now turn off the computer, and when I turn it back on, everything's back. I'm going to pause for a second and see if there's any questions before we move on to networking. You guys all good? Go ahead. The RAM is faster than the computer, yep. And so that's the reason why we always use RAM when we are working with data directly. We always read a copy from the drive and write it up into RAM. And we're making all the changes up in RAM because it's just much faster to do it that way. Yeah. Cool, great question. How's everybody doing in Slack? You guys doing good in Slack? Sean is asking, does it make sense? Makes sense. Everybody's happy. Awesome. So now we have enough understanding of how computers work so that we can now talk about how they network together. A computer with its operating system and its storage, there's a lot of power in that. But the real power of computers is unlocked when we network computers together so they communicate with one another over distances. Now, in networking, I am going to show you the basics today. For many of you, You will feel the fire hose effect today. If you have not yet, for many of you, it's going to start now. And I am only covering the fundamentals of networking. I'm leaving a lot of detail out. There's no way I can make you an expert in networking in an afternoon. And in fact, if we really started talking about networking and started doing a deeper dive, we could literally come here every day, 8 hours a day, 5 days a week for a month, and still not cover everything that we would want to know about the internet. We're not going to do that. We're going to cover all of this in just an afternoon. And so if you want to do further reading on networking, there's a lot of other materials. You will not need any of these for the exam. Remember, the exam questions are all written out of the materials here. So all you need is what we're discussing here. But if you'd like to know more about networking, there's a lot more information out there. So let's talk about what a network is. The definition of a network is simply that it's two or more computing devices connected together in some form or fashion to facilitate communication and exchange data. That's literally full stop, that's a network. Which means if I take this computer and I plug in a cable into this computer and take the other end of that cable and plug it into another computer, I have a network, right? So here I've got my cable. I take one end, I plug it into this computer. I have another computer. Let's say this is a computer right here. I plug it into that computer. I have a network. Great. I have a cell phone here and I connect this cell phone to earbuds. Well, isn't that technically a network as well? The earbuds would be a computer. It's an IoT device. That's a network. That's a personal area network at that point. If I took this floppy disk and I plugged it into this machine, which I don't have a drive, but let's say I do. I put that into the drive. I copy some ones and zeros over this disk in the form of a file. I walk it over to another computer. So I walk it over to Jose's computer. I plug it into his computer. He doesn't have a floppy disk drive either. I would have been impressed if he showed up with a computer that had one, but then I'd be surprised he'd be able to do the labs. And so isn't that a network? Two computing devices connected together in some form and fashion. What was the connection in this case? Me. I'm the connector, right? Data exchanged from this computer over to that computer. That's a network. In fact, do you know what that's called? It's called a sneaker net. But I guess in my case, it would be a Birkin net because I wear Birkenstocks, right? Yeah, those are the jokes, people. It's a Birkin net. But yes, that is a network. Now, preferably, the network is going to be reliable and fast and secure, but the size and the connection method doesn't matter. Let's talk about back in the 60s when they first started networking computers together. Let's talk about a certain project where they were trying to connect computers together to make a network. Yes, they did that. But do you know what they decided these groups wanted to do? Was several groups got together and said, hey, what if we connect our networks, our separate networks, to each other? What if I make a network of networks? The idea of the internet was born. You guys want to see a baby picture of the internet? I have one. You guys ready? It made a cute baby. Oh my goodness, was it a cute baby? Here we go. We've got a baby picture of the internet. Oh, isn't it cute? What are we looking at here? So let's zoom in on this area right over here. All the actions right here. 4 organizations got together and said, hey, let's run cable between our facilities and create a network of networks. The 4 organizations were the University of Utah, Stanford Research Institute, University of California, Santa Barbara, and UCLA. Oh, you will not see LA. That's a BoJack Horseman reference, Tim. Now Tim has to watch BoJack Horseman. Yeah. Oh, you will not see LA. One of the characters wanted to go to UCLA And her mom said, "You will not see LA." That's BoJack Horseman. Yeah. Remember that horse looking guy on my desktop earlier? That's BoJack. Yeah. Now, so of those 4 organizations, did they have something in common? What were they? They're all universities. Yeah. And they're all public universities. Now, what is the primary mission of a university? Not what is the mission statement of the university, but what's the primary mission of an organization that is a university? Universities simply acquire and share information. That's what a university does. So now, as these 4 universities, all with the same mission, collaborating to do the same thing together, and they're working together to accomplish this goal, where do you think their level of trust was between them? Was it a very high level of trust or a very low level of trust? I'll answer for you. It was high, right? Because they're all working on the same thing together. We're collaborating. We need that speed of trust to be able to do this. So when they attempted to do this, where do you think they put the security into this network of networks? Security. There's no need for security because we all trust one another. We're all amigos here. We don't have to have security. It was so hard to do. They were just happy that it worked. Literally, the first link between these institutions was UCLA to Stanford Research Institute. They got a line set up where the 2 computers were communicating with one another, and they literally were on the phone with one another and said, "I'm pressing the letter C right now. Do you see this letter C on your screen?" They see the letter C on their screen. Yes, we did it. Whoa. No, that's Arsenio. That was 2 decades after that. So now they were like groovy, man, because it was a bunch of pot smoking hippies. It was the 60s. And that is not a joke. They were a bunch of pot smoking hippies because they were, they worked at public universities, and they are smart people. That just screams smoking pot. It does, guaranteed. There's a reason why universities, especially medical universities, do not do drug testing on their principal investigators. They'd lose some really good ones. Yeah. So don't find out. We don't want to know what that professor is doing because we would lose our federal grant funding. And that is not even a joke. That is absolutely 100% true. Believe me, I worked at multiple universities. And so, yeah, we got Sean went ahead and posted BoJack. Thank you so much, Sean. So now, with these universities attempting to do this, and it was very hard to do. They needed money, they needed equipment, they needed smart people to work on it. And so they started building out this network of networks, and the Advanced Research Projects Agency of the US government, ARPA, saw what they were doing in there and said, "Hey, wow, that's interesting. We like that. We like what you're doing there. Can we have in on this?" So ARPA goes to the universities and says, "We got large buckets of money to do your research." Now, what do you think the university said? "Oh yeah, we like the government funds. Public universities are very comfortable with taking government money. They literally have offices at the universities where that office's job is just to bring in the government money." And so where do you think their level of trust was when ARPA got involved? Still very high. ARPA is our sugar daddy. They're funding our efforts. Now, ARPA became DARPA. D was Department of Defense. And so now the military was involved, and it was great because the military had even bigger buckets of money. Here's a big truckload of money to do your research. They said, "Yes, we love the money. Nom, 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 nom." They literally said nom, nom, nom. No, they probably didn't. I don't know. It was probably more groovy, man. So now there started to become a concern. Well, the military's involved and we trust them. They're giving us money to do this work. But what if the military decided one day, "Yeah, all that work that you guys did, yeah, it's not yours anymore, it's mine. and you don't get any of it. Well, could the military do that? Yeah, they're the military. They get to take what they want. If that's what they want, that's what they take. So that thought kept up one of the researchers at night, Steve Crocker. Steve Crocker, as a young man and researcher in Southern California, living in Southern California, he was in a small studio apartment because he's on a university salary. And he's living in the small studio apartment with his new bride and young infant child. It woke him up in the middle of the night. What if the military comes in and says, all of this is ours, and then we're left with nothing? He couldn't get back to sleep. And he decided, I just need to get up out of bed and start trying to solve this problem. So he gets up out of bed and goes into the one room of their studio apartment that he could go into and turn on the light. It was the bathroom. And so he shuts the door, turns on the light. He sits down on the toilet. I believe the seat was down. I don't know state of dress. By the way, folks, I don't make any stories up. These are all true. He sits down on the toilet. He has a clipboard with some papers on it and a pen. He writes at the top of the document. He writes the words request for comment. And then he starts writing out what they've built so far. And that request for comment document became the start of documentation of the internet. We know them now as RFCs, and it's documentation where we have documented what it is. Antonio, thanks so much for the why the long face reference with Bojack. That's an awesome reference. So here we can see, here is RFC number 1, the thing that started it all. Now, back then in 1969, the network they were building was called the IMP software network. And you'll see that the document just basically states what their purpose was, what they were trying to do. And then they described, we are going to transmit information in this format. We are going to have a 5-bit address to send data to. So every computer on the network will have an address, and that address is in a 5-bit format. And then we've got 8 bits for a link between the two machines so that they know that they can find each other there. A trace bit and 2 spare bits. Wait, 2 spares. Why did they build an extra space? Well, for 2 reasons. One, 16 bits is 2 bytes, right? And so they rounded to the nearest byte, 2 bytes. And they said, well, let's hang on to these 2 extra bits. We've used 14 of them so far. We'll hang on to these 2 extra bits because there might be a need for them. Since it rounds up to 2 bytes, that's just convenient for us. So we'll keep those as spare, just in case. But this was the start of, now that we've talked about binary, you guys understand this part, right? These are just numeric values for addresses and for maintaining a link. Cool. Now, let's go back to the slides here. There we go. There was no need for security because we all trust one another. And the thought was there would only be a few thousand computers. 5 bits doesn't give you a whole lot of address space, right? And that was the idea. It wasn't going to be very scalable into the future. They figured we're just going to at most connect maybe a few thousand machines. The idea was to build a self-healing network, which means that if one of those links went down, the others would still be able to operate. If traffic was flowing through one of those links, and now that link goes down, that's okay. We'll just find another way around it. And so as long as we've got a bunch of different links for redundancy, we can go around any problems, and we can put new systems on without having to reconfigure things. We can take old systems off without reconfiguring them. And so it made it very scalable. Now, let's fast forward into the future here, and let's talk about the protocol that was built to replace all of these others that they were working on. It's called TCP/IP. TCP/IP is what we use on the internet today, and it stands for Transport Control Protocol, Internet Protocol. And it describes a packet switched network. What that means is that I have pieces of information I want to send from one computer going to another. Now, those two computers are connected together, and notice there's multiple links, multiple paths that we could take. And as it sends, the sending computer, host 1, sends it to host 2, well, those packets of information could take different paths. And they could then come out of order. TCP had to be aware of that. I sent packets 1, 2, and 3 to you. When you receive those packets, you need to know that you received 3 of the 3 and that they're in the right order. And if they're not in the right order, we'll just reassemble them in the right order. So now host 2 can verify, yes, they received everything host 1 sent, and host 2 can put them in the right order. That's what TCP/IP did. Vint Cerf and Bob Kahn created this. It was an RFC. Let me go ahead and show you the RFC for IP version 4. And Sean, if you would post RFC for version 4 as well in Slack, I'd appreciate it. So RFC for IPv4. And you'll see that's just an open source document. It was the 791st document. So there's lots of documentation that describes lots of different things. But now we can see that TCP/IP in version 4, I'm going to scroll down a little bit here and go to the header of TCP/IP4, which we'll talk about in just a little bit, but I just want to show you this document where it spells out there's a 4-byte long field. So 0 through the bit 31, that's 32 bits, 4 bytes across. That's why we were talking about the importance of 4-byte numbers earlier, is that's how we keep track of networking, is through 4-byte groups. And then it's got things like a sending address, the source address, and the receiving address, and a whole bunch of other information that describes what these packets of information should be. So each packet of information is simply a self-contained piece of data that can flow across the network from the sender to the receiver. And it's got all the information that needs to actually get to the recipient. All right, great. That allows us to scale this to infinity. So now these networks can get bigger and bigger. Now let's talk about what the internet is and what it means to be on the World Wide Web. The internet is literally just a word that means the network between the networks. I have a network, you have a network, we are sending packets between them. The network between our two networks is the internet, the network between the networks. Now, World Wide Web is one way for us to request and receive web pages, and that was created by Tim Berners-Lee, and he invented this in 1989. He was knighted for his work by the Queen, so now he is Sir Tim Berners-Lee. He created this process of web servers and web browsers as a concept, and so that we can request web pages from other machines and they can send us those web pages. Great. So in 1995, when the internet really exploded on the commercial market, we went from tens of thousands of users to millions of users, and then tens of millions, hundreds of millions, billions. Now, today, there are over 5 billion users on the internet. Where do you think our level of trust is now? Is it very high? Rennie says very high, and he's smiling like, yeah, right, evil Rennie, I believe you. Do you have 5 billion friends that you know and trust? No. So where's the trust now? Very low. What did they do in changing the protocols to account for that lack of trust? Nothing. Don't touch it, you'll break it. And so literally what they built with TCP/IP, with no security built into it, we're using that on the internet today. And we can't trust people on the internet today. That's okay. We're going to solve that problem tomorrow. But the internet was built to be insecure by design. It wasn't even an accident. They said, this is the way we're going to do it. I don't care if that level of trust has changed, because what we can't do is we can't just go deciding to change a protocol, because these protocols, the reason why those RFCs are so important is because they are describing how two computers need to communicate. And if these two computers don't have the same set of rules to communicate, they won't be able to communicate. So we can't just change the protocols, or we would break the internet if we changed the protocols. So they said, don't touch it, you'll break it. It's fine that we don't have this trust. Encryption is how we'll fix that. So that's tomorrow's conversation. But let's talk about the internet, the World Wide Web, and TCP/IP. I just threw a whole bunch of different terms at you. What does it mean when I say the internet? What does it mean when I say TCP/IP? So the internet, think of the internet as, say, the US highway system. And the US highway system connects cities together. I always found it very fascinating that there is, though I am a long way from home in Denver, there is a contiguous piece of pavement between the front door of this hotel and the front door of my house. Isn't that cool? It's the US highway system. Now, technically, the internet, all of those series of connections don't follow exactly the US highway system. They follow something else. Do you know what they're actually following? Is the US railway system. I don't know who to attribute this to, but it was an ingenious move. Whereas as the 90s and the early 2000s progressed, we had realized that a lot of the infrastructure that we built 50 years ago, that was the US railway system, a lot of that needed to be replaced. That stuff gets old, it wears out, and they needed to refresh it. And so somebody had the idea, while we're refreshing all of those tracks, why don't we run conduit under the tracks? And so we can put cables under there. Great, so now we've got these cables under the railway system that's connecting all of the cities together. And then out on the rest of the world, how do we communicate across oceans? Here I've got an example of the cabling system that sits underneath the seas. So we've got all of the continents connected together, and then on land, it's basically going over the land. So lots of connections. Question, if I send information across the internet, will I necessarily know what path it takes? I have no idea. Would my packet of information that's going to you, could it go through Russia? Could it go through China? Could it go through other areas that I don't trust? Yeah. Well, that's a problem to solve for later. But the point is, when you send information out on the internet, you don't actually know where it's been. Now, the internet is the highway system. TCP/IP, think of that as the truck. It's that transport mechanism that goes over the highway. And so while the highway, the road, is the internet, TCP/IP is the truck that is going over that highway. And web traffic, World Wide Web, that's just one type of cargo that can go in this truck. So now, this truck doesn't care what it's transporting. Is it Amazon stuff? Is it letters to Santa Claus? Whatever it is, we can put anything we want in that truck, right? Web traffic is just one type of cargo that can go in that truck. Now, whoops, I clicked off my screen over here, so my clicker pointer thingy isn't working. So in order to have these computers communicate with one another in some sort of meaningful fashion, there needs to be rules. The rules are what we call protocols. Protocol is just a fancy word for some rules that we have in place for communication. Now, here in the classroom, we have a set of protocols that we've been using. First, when we walked into the classroom yesterday morning, we used a protocol that's like a networking protocol. I was making sounds with my mouth, right? So we're using a wireless communications, not Wi-Fi. It's that I'm making sounds with my mouth and you're hearing those sounds with your ear. So that's a protocol. Now, what did I put on top of that protocol is another protocol called the English language. I put sounds together in a certain way that made words. And I put those words in a certain order that make sentences. And then I use those sentences to convey intellectual concepts to you. Great. So the English language was a protocol sitting on top of my making sounds with my mouth. Now I could change any one protocol, but if I change the protocol, you must also understand the other protocol that I change. Does anybody here speak Russian? Nobody speaks Russian. So what I'm going to do is I'm going to change the protocol from English to Russian. If I started speaking Russian, which I won't because I can't, you would still hear the sounds that I'm making with my mouth, but you would lose meaning because you understand English and I'm speaking in Russian. See, we have to use the same protocols. Computers are the same way. If one computer is speaking one language, the other computer has to understand that language. But now notice, I could also change that layer underneath my speaking. What if instead of speaking, I started writing? I'm writing in English, but now I've changed that other layer. I am writing instead of speaking. So each one of these protocols, they're stacked together. And we need to have alignment in that stack where we're all using the same stack to communicate. So now, that's what's referred to as a protocol stack. We're going to get to that in a little bit based on, we'll probably get to that before lunch here. We're in good shape. Okay. Now, in the documentation that created the internet, these are all in those requests for comments. What Steve Crocker was trying to do is just simply document what we've created so far. But what he really started was a revolution of how we documented how computers communicate. So now these RFCs are not only defining what we do, but it sets those rules of communication. So if two computers need to communicate with one another, all they have to do is follow the rules that are in the RFC, and it doesn't matter what vendor they are. I have an HP laptop. My computer is communicating to Jose's computer. He is using an Apple Mac OS computer. That's okay that they're two different vendors making two different sets of hardware with two different operating systems. Because as long as we follow the rules in the RFC for networking, the two will be able to send and receive information to one another. Great. Now let's talk about those stacks of protocols. There's different types of protocols. There's networking protocols like the Ethernet protocol and the Internet protocol, IP. There's also application protocols. An application protocol doesn't mean Word or PDF or Excel. With application here, we mean, what is the reason for communications? Are we sending an email? That would be SMTP, Simple Mail Transfer Protocol. Or am I requesting a web page and want to receive a web page in return? That would be HTTP, Hypertext Transfer Protocol. Now, since the internet didn't have any sort of security built into it, we had to add security on. So there's also security protocols. There is IP security. IPsec was created to help the internet protocol that was insecure add security in the form of encryption. And IPsec is what we use for the many uses, but one of them that's the most common is VPNs, virtual private networks. But then there's also for HTTP web pages, I could send a request, HTTP plain text over the internet. Wait a minute. If I don't know where my packets have been, do I want to send that information plain text? What if the Chinese or the Russians or the Americans, they're all, yeah, I'm going to lump those Americans in there as well. And so what if I don't want those other groups seeing my information because I am doing e-commerce, I am sending credit card information. I want to protect that communications using SSL or TLS, stands for Secure Sockets Layer, Transport Layer Security. We are going to talk about every single one of these protocols on this slide in turn, all right, over the next 2 days. But this is just an introduction of the types of protocols, and I am going to stack them together just like I stacked I'm speaking to you and you're hearing, and I stacked English on top of that. We asked ourselves, well, what would we need in order to network two computers together? What stacks do they have? And so smart people, they got together and they asked themselves, what is the things that we need and how do they stack together? How do they fit together? And they said, well, first, we need to have a physical connection between them. In this case, I've got this cable. It's a copper cable. It's got 4 pairs of copper twisted inside. And so it's a twisted pair cable is what they call it. This one's a Cat 5, category 5, and it's got RJ45 jacks on the end. So that is a physical cable. That's layer 1. I need a physical medium to transmit through. Okay, what else do I need? They thought about it and they said, well, what flows over this copper cable? I need some sort of a data link layer. And with that data link layer, I need to have hardware addresses for the things that are plugged into the ends of this. So I plug an end into one device and I plug the other end into another device. The two need to be able to find each other and uniquely identify each other so that they know that they're talking over this copper cable. So that's the data link layer. And protocols like the Ethernet protocol will flow over this copper cable. Okay, great. So Ethernet was the data link. The copper cable was the physical layer 1. And they said, well, what else do we need? And they said, well, here's the thing. In order to have a network, I would either have to run a single cable between every computer that ever needed to communicate. That's inefficient. Or I will send data from one computer with a final destination, a recipient, someplace else. So I need a semblance of a network. Yeah, because these computers aren't always directly connected to one another. And so I need some sort of an internet protocol. And I need to be able to route those packets from one location to another. Okay, so network layer, layer 3, stacked on top of 2 and 1. And they said, well, what else do we need? Now, as these two computers are networked together, well, that's one thing that they can find each other across this network. How are they going to transport information to one another? So the transport layer is where protocols, and we're going to discuss these two protocols this afternoon, TCP and UDP, are protocols that allow me to send information from my computer and you receive that information and you know that I was the one that sent it. And now we've got a transport mechanism between the two. Okay, cool. What else do we need? Well, when these two computers are sending and receiving information to and from one another, we need to have some semblance of a session, because when I send data to you and you send a response in return, I need to know that that response was to my original request. Okay, so I need a session layer to start communications and to manage that communications and to end it. Very much like us talking, meet in the hallway. Hey, how you doing, Rennie? Rennie says, I'm doing fine. Great, I'll see you in class. Rennie says, I'll see you there. That was a session. All of that communications was related to one another. All right, what else do we need? Well, now remember, Jose's computer was an Apple Mac OS operating system. Mine's a Windows operating system. What if the way my Windows machine understands information is different than how Jose's machine understands it? We need to make sure that we're reading the information in the right order and that when I send that information, it makes sense to him. So a presentation layer. Okay, great. What else do we need? That should be it, right? Oh, the application, the whole reason that we're talking. What are we doing? Am I requesting a web page of Jose's web server? Am I sending him an email? That's the application layer. The whole reason we're even networking computers to begin with. That's the important part, right? That piece. So now you've got this 7-layer stack. And it's referred to as the OSI, the Open Systems Interconnect stack. And that model, the OSI model, is managed by a nonprofit organization called ISO, the International Standards Organization, because it's not confusing at all to say the ISO OSI model, right? I'm not the one that made these acronyms up. Don't be angry at me. But the International Standards Organization manages this OSI stack. Now, you may have at some point in time have heard a network engineer refer to a problem as a layer 8 issue. Well, is there a layer 8 here? Not officially, but technically when those people talk about a layer 8 issue, they're talking about the user. They're talking about the person was the problem, not the network. It was the person sitting at the chair. It was an ID10T error. If you don't know what that is, spell it out, ID10T. Or it was a PEBCAC error. Problem exists between keyboard and chair, right? It's the person. And then some will say that 9 and 10 are money and politics. Those are all jokes, but things that you'll hear referenced. Now, when it comes to actually implementing networking, it turns out that these 7 layers aren't all separate, discrete layers. Turns out that some of them are kind of smushed together. And so, for example, with the physical layer and the data link layer, I have this physical copper cable, and I will always use the Ethernet protocol over this copper cable. And so Ethernet is layer 2, the copper cable is layer 1. Well, that's my link layer. And so 2 and 1 are kind of squished together, and we just call it layer 2 communications. So I'm going to, next to the link here, for those taking notes, this is called layer 2 link layer. Now, my network layer is where my internet protocol addresses, my IP addresses sit. And so that's really just layer 3 is layer 3, no problem. But then moving up the stack here, the transport layer is taking care of transport, but it also kind of manages the session for us. That session for computers of beginning the communications. I want to communicate with you. Do you want to communicate with me? Yes, we're talking. Okay, now we're talking. Now let's talk. And then, hey, I'm done talking to you. Are you done talking to me? Okay, now we're done talking. That's a session. Me and Rennie in the hallway. It was like, hey, how you doing? I'm doing good. How about yourself? I'll see you in class. That was a session. So now the transport layer takes care of some of that session at the computer level. And so layer 4 transport layer is the transport layer plus a little bit of that session. But now the rest of the session and everything up to the application, it turns out that the application layer and the presentation layer and the session layer of people signing into a website and then logging out, whatever they're doing, all of that is managed by the application itself. And so anything above that session is the application layer. And so we call that all 7. The reason why this is important is because when we talk about networking, we use the OSI layers. But when we implement networking, there's really only 4 separate discrete layers. But we number them as if all 7 exist. So whenever I'm talking about layer 2, I'm talking about layer 2 and layer 1. And Tony asked, no layer 1? Yes, there is a layer 1. It's part of layer 2. And so whenever I say layer 2 communications, it means 2 and 1. And whenever I'm talking about layer 7 application layer, it's application and presentation and session. Cool. So now, one of my favorite demonstrations in this entire course is this one right here, where we are going to have that stack just fall over on its side, go crash. I love that. Isn't that cool? Why did I do it again? One more time. All right. So I've got my 4 layers. It's going to fall over on its side, crash. Now, My application data is just simply something like I am making a request for a web page. That's what I want to send to your web server, is this request for this web page. Well, in order for me to send that request to your web server, I need to have a layer 4 header. So, and you can, for those taking notes, just go ahead and number them right here, 7 and 4 and 3 and 2. So now I am going to encapsulate this layer 7 data by putting a layer 4 header in front of it. That's what's encapsulation is called. I'm just simply putting some data in front of the data. So I have layer 4 data for this layer 7 application data. And then I need to put a layer 3 header in front of that. So I'm encapsulating with layer 3, I'm encapsulating 4 and 7. And then I'm going to put a layer 2 hardware header on it as well. And this makes what we call a packet of information. That demonstration earlier of the packet switch network where you had those 3 blocks going around, each block had all of this information of the layer 2 hardware header, the layer 3 IP address, the layer 4 transport header, and the layer 7 data. So each one of those pieces contain all of the information that they need in order to go from one computer to another. Great. Now, some of you may have heard or will hear a word that sounds like it's a packet. It's called a frame. I want to clarify. When you have layers 3 through 7 together, that's referred to as a packet. But when you add that layer 2 header, some people will then refer to that as a frame. And so your network engineers, when they're talking about frames, they're talking about the layer 3 through 7 data headers, plus that layer 2 header as well. All right, so now I've given you a lot of detail. I'm going to simplify things. I am going to explain how the US Postal Service works to you. Before Instagram, when dinosaurs roamed the earth, humans were communicating by taking a primitive crushed tree substrate. They would crush it, they would bleach it, and then it's paper, right? Yeah, and then they would take a primitive carbon scribe, a pencil, and they would write messages to one another. And then you would fold up that piece of paper. You would put that piece of paper into another specially folded piece of paper called an envelope. I'm describing writing a letter, right? I write a letter, I put this piece of paper in an envelope, and then I write information on the front of the envelope. What do I write on the front of the envelope? A to address, a from address. I got to put a stamp on it. Well, that to address, that from address, the stamp, isn't that like the headers of a packet? Yeah, the information on the front of the envelope, think of that as a header, and the information inside the envelope, that's layer 7 data, right? You wrote a letter and you have to put headers. That's encapsulation. I encapsulated this piece of paper inside of an envelope, and the headers were the encapsulation. Pretty simple, right? Now, I am going to mail this letter. Let's talk about how the US Postal Service works. It was really fun. About a year ago, I was teaching this class to the US Postal Service. And they said to me, I learned a few things from them. They learned a few things from me. But they said, yeah, the examples that you're giving here, that's not exactly how it works. And I said, you're right. The way I'm describing it is much more efficient than the way you do it. So those are the jokes here. And yeah, we actually, okay. Now we're going to simplify. I am going to write a letter. I am going to put it in the envelope. I am going to write a to and from address, and then I put that letter into a mailbox. It sits there until a letter carrier comes by and picks that up. Now, does the letter carrier come by and look at the address and say, oh, I know where that goes, and they walk it over to the other location and they send it to they give it to the other person? No. Are they even looking at the address that's going to? They don't care. As long as it's got a stamp on it, they're going to pick it up. If it's got a to address and a stamp, they're like, okay, fine. And they take all of those letters to their local post office. Now, the local post office is going to look at that to address and they're going to ask, well, where should that go? That's not anybody at our post office. That's someplace else. And I don't know where that is. So I'm going to send it to a sorting center, and the sorting center is going to figure it out. Now, the sorting center looks at that to address, and based on that address, they say, oh, that address is a delivery point. The U.S. Postal Service calls it a delivery point that goes to a certain post office. And so now they send it to this other post office. That post office looks at that address and says, oh, yeah, well, based on that address, we put it on a certain letter carrier's route going to that delivery point, that home. And so now it's put in their mailbox. They pick it up, they open it up, they can see the letter. I didn't lose anybody so far here, right? Just pretty simple, straightforward stuff. Now, did the postal worker even look at the from address and say, oh, this is the address I'm picking this up from? Did they even bother to do that? No, they don't care. I could write a letter going to my home in Denver, and I could put any address as the from address. They're still going to pick it up from this hotel here. They're not going to bother to check that from address. And in fact, if I put no from address, they're still going to pick it up and attempt to deliver it, right? Now, let's go a little bit bigger picture here. I am going to mail a letter from Los Angeles going to an address in Houston. So first steps, the same as before. I write the letter, I put the information on the front of the envelope, I put it in a mailbox. Letter carrier comes by, picks it up, and takes it to the post office. They don't know where this letter is going, they don't care. They're just taking it to the post office. Now the post office is going to look at that address and say, you know what? I don't know where Houston, Texas is. I mean, the postal workers obviously know where Houston, Texas is, but they don't know how to get it there. All they know is they send it to their citywide sorting center in Los Angeles. Now, the citywide sorting center in Los Angeles looks at the address and says, yeah, that's no place in Los Angeles here. So we're going to send it to the statewide sorting center in San Francisco. San Francisco looks at this and says, yeah, this address, that's not even in the state of California. So we're going to send it to our region-wide sorting center in Denver, Colorado. And I used to drive past this region-wide center on my way to work at the university. It's a huge campus with trucks, just big semi-trucks with tons of mail going in and out of it constantly. There's a 6-lane road, and there's a stoplight on that 6-lane road just for trucks going in and out of that facility. So lots of mail going in and out. And now the Denver region-wide sorting center looks at that address and goes, oh, based on this address, that goes to Texas. And so they send it to the statewide sorting center for Texas in Dallas. Dallas looks at that address and says, yeah, based on that address, that goes to the city of Houston. So they send it to the sorting center in Houston. Houston receives this and says, yeah, based on that address, it goes to this particular post office. And then that post office says, yep, that delivery point is on this letter carrier's route. They give it to that letter carrier, and that letter carrier takes it to the house, the delivery point. Everybody get that? Great, because now you know how the internet works. That's literally how the internet works. Let's change some names here. Instead of post office and sorting centers, let's put some technical terms to it. Your mailbox at your home is basically your internet connection to your ISP, your internet service provider, right? And isn't then your ISP like your local post office? Use any information going out to the internet, you send it to them. Now your ISP will look at these packets of information and say, oh, do you know what? I don't even handle that. That's not anybody for our ISP. And so your ISP has ISPs. They have internet service providers. Companies you've probably never heard of, like Hurricane Electric, UUNet, Level 3 Communications. And so those ISPs to your ISP, they are routing the traffic on what we call the backbone of the internet. The backbone of the internet is just those series of routers that connect all of these cities to one another. And the idea of the backbone of the internet is to find an efficient path getting to its final physical location. And so each router on the internet is going to get it closer and closer geographically, but the closest geographic location might not be the one that makes the most sense. What they actually do is they forward it based on what they call the least cost route. What is the most efficient way to get it there? Now, if I am sending a packet of information from Washington, D.C., going to Denver, Colorado, if it's a letter in the Postal Service, the U.S. Postal Service is not going to send it outside the U.S., right? It's just going to stay inside of U.S. because it's a U.S.-based address. But if I send a packet out on the internet, am I assured that that packet stays in the U.S.? I got no idea. Did I define where it should go? No, I just put a to address. I said, this is the recipient. You guys figure it out. And so that least cost route might be it goes from here to London, and from London it goes to Paris, and then to Prague, and then over to Dammam, Saudi Arabia, and then across China over to Singapore, and then maybe Singapore up to Japan, Japan to San Francisco, and then from San Francisco to Denver. And that might have been a more efficient route than sending it from DC up to Chicago, and then over to St. Louis, and then over to Denver. That might have been inefficient. And so it's not always the closest geographic route. It's whatever is the least cost route. And these routers on the internet, these ISPs to the ISPs, they broker this traffic between one another. And so they make those decisions. You don't get to make those. How's everybody feeling? Good? Do you know what? We're a couple minutes early. I don't want to start the next concept until after lunch. And so you get a few extra minutes for lunch. We all decided, nobody came to me and said that 60 minutes isn't feasible. So let's do a 60-minute lunch. We're taking lunch at 12:15. I'm giving you 2 extra minutes. We'll come back at 1:15. See you at 1:15 Eastern time. Have a good lunch.